Again, welcome to chemistry classes by Vijay Kumar Sethi, class 11th chemistry. We were discussing unit 6 thermodynamics, and in this video we will discuss about internal energy and mathematical statement of the first law of thermodynamics. First, internal energy. This is represented by U, capital U. The total energy of the system is called internal energy of the system. Total energy. Okay, and this energy include different types of energy. That's why we can say it is the sum of kinetic energy. And again, kinetic energy may be translational energy, vibrational energy, and rotational energy. Potential energy, chemical energy, electrical, mechanical energies, etc. Simply we can say all types of energies constitute internal energy of the system. Internal energy is a state function. It means it depends on initial and final states of the system. Absolute value of internal energy cannot be determined. Why? Because this is the sum of a number of energies, and absolute values of these energies cannot be determined. That's why absolute value of internal energy cannot be determined. But change in internal energy, that is delta U, is determined, and this is given as delta U is equal to U2 minus U1. We can say this is U1, this is the internal energy is in state 1, and U2, this is the internal energy in state 2. Difference of this is given as delta U. It may change when heat passes into or out of the system, work is done on or by the system, matter enters or leaves the system. Now, ways of changing internal energy. How can we change the internal energy? We will discuss two ways. One is work, another one is heat. First come to the work. Consider an adiabatic system. We already discussed in the previous video what is the meaning of this adiabatic system. Okay, in this system, matter and energy is not exchanged with the surrounding, but internal energy can be changed by work. Is it clear? And we can say this is the system in which heat remains constant, but internal energy changes by work. Initial state of the system is represented as A and its temperature is TA. And internal energy of the system in state A is given by UA. We can change the state of the system in two different ways. First one, that is one way is by mechanical work. Suppose if 1 kilojoule amount of mechanical work is done by rotating a set of small pedals and we try to change its temperature, then system will reach in the final state, and this is represented as B state, and its temperature is TB. If this TB, that is temperature in the final state, is greater than TA, then that's why we can say change in temperature is given as delta T is equal to TB minus TA. The internal energy of the system in state B is given as UB, and hence change in internal energy delta U is equal to UB minus UA. Clear? And this change in internal energy is equal to W. W is a work, and this AD representing that this is work is done in adiabatic process. Okay, that is heat remains constant but internal energy is changing by work. Okay, there is a second way. We now do an equal amount, that is 1 kilojoule of electrical work with the help of an immersion rod. I think you are familiar with this immersion rod. This is used to we can say that is to give the hot water. Is it clear? This is the immersion rod. And note down the temperature change. We find that the change in temperature is same as in the earlier case, that is in case of mechanical work, that is TB minus TA. That's why change in internal energy is given again delta U is equal to UB minus UA, and in this case again this W is adiabatic process. Okay, this is the internal energy change in the one way, and this internal energy change the same in this second way, okay, when we are doing electrical work. Therefore internal energy of the system is a state function. Okay, whatever the way you are using to change this internal energy, it may be mechanical work or it may be electrical work, but delta U remains the same. That's why internal energy of the system is a state function. J.P. Joule showed that a given amount of work done on the system, no matter how it was done, irrespective of path, produced the same change of state as measured by the change in temperature of the system. Is it clear? And by international conventions, work done on the system, clear, work done on the system is considered as positive work and written as plus W, and in this case internal energy of system increases. And work done by the system is considered as negative work written as minus W, and in this case internal energy of the system decreases. Okay, now this is the another way by changing internal energy, that is by heat. If system and surroundings are at different temperatures, internal energy of the system is changed by transfer of heat through thermally conducting walls. Okay, if temperature of the system is TA and temperature of the surrounding is TB, and if TB is less than TA, that is we can say temperature of the system is more, then heat is transferred from system to surroundings till temperature of both system and surroundings becomes equal. Okay, that is TB is equal to TA. And if TB is greater than TA, then what happens? Heat is transferred from surroundings to system till TB is equal to TA. In this case, change in internal energy, that is delta U, is equal to Q, that is change of heat, when no work is done at constant volume. Okay, this is a system which allows heat transfer through its boundary. By conventions, the Q is positive when heat is transferred from the surroundings to the system. Clear? When heat is transferred surroundings to the system, Q is taken as positive, plus Q, and in this case the internal energy of the system increases, and Q is negative, that is minus Q, when heat is transferred from system to the surroundings, resulting in decrease of the internal energy of the system. In this way, we can change the internal energy of the system either by work or by transfer of heat. Now, mathematical statement of the first law of thermodynamics. Consider initial state of a system. In this, its internal energy is U1. If Q amount of heat is supplied to the system, that's why we are writing that is plus Q, then its internal energy becomes U1 plus Q. Then again, W amount of work is done on the system. Okay, on the system, that's why we are taking as a plus W. Then we reached into the final state, and its internal energy is represented as U2. Then we can say U2 is equal to U1 plus Q plus W, and change in internal energy, that is delta U, is U2 minus U1, and this is equal to Q plus W from this. Okay, and this delta U is equal to Q plus W. This relationship is known as mathematical statement of the first law of thermodynamics. Clear? Remember it. This is the one important derivation and relation. Delta U is equal to Q plus W, and which states that the energy of an isolated system is constant, and it is commonly stated as the law of conservation of energy. Simply we can say state of Mathematical statement of the first law of thermodynamics and statement for the law of conservation of energy is same. Energy can neither be created nor be destroyed. Q and W are path functions. If we consider separate, then Q and W are path function, but Q plus W, which is equal to delta U, will depend only on initial and final state. Therefore, Q plus W is state function. Okay. It will be independent of the way the change is carried out. If there is no transfer of energy as heat or as work, that is isolated system, that is if W is equal to 0 and Q is equal to 0, then we can say delta U is equal to 0. Now see, there is one question, problem 6.1. Express the change in internal energy of a system when no heat is absorbed by the system from the surroundings, but work, that is W, is done on the system. What type of wall does the system have? Now see, no heat is absorbed, but work is done on the system. That's why we can say actually this is the adiabatic system. In this case, this is delta U is equal to W adiabatic. And what is the wall? What is the type of wall? Wall is adiabatic wall. In this case, heat can exchange, but internal energy is also changing by doing work. Okay. No work is done on the system, but Q amount of heat is taken out from the system and given to the surroundings. What type of wall does the system have? No work is done. That is W is equal to 0. When W is equal to 0, we can say again we have discussed the relationship, that is this is delta U is equal to Q plus W. So this W is equal to 0 and Q amount of heat is taken out from the system. That's why this Q will be considered as minus Q. That's why we can say delta U is equal to minus Q. And in this case, the thermally conducting walls are there. Next one is W amount of work is done by the system. That's why this will be taken as a minus W. Work done by the system is negative. And Q amount of heat is supplied to the system. That's why Q is taken as plus Q. Okay. What type of system would it be? Delta U is equal to Q minus W, because Q heat is supplied to the system, that's why this is plus Q, and work done by the system, this is taken as a negative, that's why this is minus W, and this is a closed system. Is it clear? Thank you. Subscribe my channel to get the new videos from this chapter.